Hello, in this video we're going to be talking about AP Chemistry's topic 1.8, valence electrons and ionic compounds. So just a reminder, on the periodic table there is a division on the periodic table, and that line divides the metals, which are over on the left hand side, from the nonmetals, which are on the right hand side. And the behavior of the metals and nonmetals is completely dependent on the effective charge of the metals versus the nonmetals. Metals tend to have a low effective charge, meaning that the nucleus does not pull on the electrons as strongly as the nonmetals, which tend to have a high effective charge. And so a high effective charge means that the valence electrons are pulled more strongly to the nucleus. So just to give you a quick example, if we looked at magnesium, the way that we calculate effective charge is the number of protons. In this case, magnesium has 12 protons, minus the number of core electrons. And magnesium has two valence electrons because it's in the second column on the periodic table, meaning that it has an S1 and S2 electron, two valence electrons. So all the rest of the electrons are core electrons. So if there were 12 electrons, 10 of them were core electrons because 2 were valence electrons. So the effective charge on magnesium is 2, meaning that the valence electrons are being pulled on by 2 protons in the nucleus. The other 10 protons are being blocked or shielded by the core electrons. If we look over here on the right-hand side, let's take chlorine for an example and calculate its effective charge. The effective charge of chlorine is the number of protons chlorine has. Chlorine has 17 total protons, and we're going to subtract how many core electrons it has. It has 17 total electrons. 7 of those, 1, 2, 3, 4, 5, 6, 7, 7 of those are valence electrons. So 17 minus 7 is 10. There are 10 core electrons, just like magnesium, 10 core electrons. But 17 minus 10 means that there are 7 protons in the nucleus not being shielded. 7 protons that are pulling on the valence electrons. That is a much stronger pull on the valence electrons than magnesium's only 2 effective charge. So high effective charge means that there's a high pull on of electrons. And so that high effective charge also creates what's called a high electronegativity. Electronegativity is the ability of an atom to pull another electron into the valence shell. So a high effective charge creates a high electronegativity. A low effective charge means that there's a low electronegativity. That means that the metals do not pull electrons to themselves very easily. So let's just remember how many valence electrons each column has. The first column, they have 1 valence electron. The second column has 2 valence electrons. And let's also call the columns by their names. This is the alkali metals. The second column, the alkaline earth metals, has 2 valence electrons. We're going to skip the transition metals because we don't talk about their valence electrons in quite the same way. Group 13, which is the aluminum family, has 3 valence electrons. The carbon family has 4 valence electrons. The nitrogen family has 5 valence electrons. The oxygen family, which is also called the chalcogens, has 6 valence electrons. The fluorine family, which is called the halogens, has 7 valence electrons. And most of the elements in the noble gases, except for helium, have 8 valence electrons. So 1 through 8 valence electrons. If you recall, atoms tend to lose or gain electrons to become isoelectric with the noble gases, to be like the noble gases. So lithium, with its 1 valence electron, will lose its 1 valence electron very easily to become isoelectric with helium, to become the same electron configuration as helium. Sodium, same thing, 1 valence electron. It loses that 1 valence electron very easily to become isoelectric with neon. Potassium loses 1 electron to become like argon. Rubidium loses 1 electron to become like krypton. So all these elements tend to lose 1 valence electron, and when they do that, they form the cation with a 1 positive charge. And because they do form the same charge, they tend to react very similarly to one another. So potassium reacts in a very similar manner that cesium reacts, or that lithium reacts. The second column, the alkaline earth metals, have 2 valence electrons. So if they lose 2 valence electrons, like magnesium loses 2 valence electrons, it becomes isoelectric with neon, has the same electron configuration as neon, which makes it more stable. So then it will have a 2 positive charge. So all the elements in the alkaline earth metals have a cation charge of 2 positive. Again, we're going to skip the transition metals. These have 3 valence electrons, so they tend to lose 3 valence electrons to become 3 positive. We're going to skip the carbon family. The nitrogen family has 5 valence electrons. But remember, they have a very high effective charge. The nonmetals have a high effective charge, so they don't really want to lose electrons because the nucleus is pulling hard on them. So they tend to gain electrons to become isoelectric with a noble gas. So nitrogen needs to gain 1, 2, 3 electrons to become isoelectric with neon. So to do that, or when it does that, it becomes 3 negative. And nitrogen and phosphorus and arsenic all do that. They gain those electrons, those 3 electrons, to become isoelectric with the noble gases. The oxygen family gains 2 electrons, 1, 2, to become isoelectric with the noble gas. And the halogens gain 1. And of course, the noble gases are already have a full valence shell, so they do not gain or lose electrons. They have no charge. So these charges are what allow metals to attract themselves to nonmetals. So metals almost always attract to nonmetals when they form ions, and if you take a metal and a nonmetal and react them with one another, they form an ionic bond. Ionic bonds are simply an attraction between the positive metal and the negative nonmetal, the cation metal and the anion nonmetal. So when a metal and nonmetal do react with one another, the metal loses electrons and forms a positive ion, the nonmetal gains electrons and forms a negative ion, and then a positive and negative ion can attract each other. So I'm gonna scroll down here, and we're gonna try a couple of examples of how this works. Well, that didn't work. Okay, so let's just use the periodic table we got. So let's take a potassium atom, and let's react it with a sulfur atom. Okay, so potassium with its 1 valence electron will lose it and form ions with a 1 positive charge. Sulfur with its 6 valence electrons will gain 2 extra electrons and form sulfur ions with a 2 negative charge. And once you have a positive and negative ion, the 2 ions can attract one another. The potassium is now going to be attracted over to the sulfur because positives and negatives attract one another, and we end up with potassium bonding to sulfur. But if you'll notice, 1 potassium ion and 1 sulfur atom are not neutral. We need compounds to be neutral. So when this ionic bond forms, it actually takes 2 potassium ions, each with a 1 positive charge, to cancel out the charge on the sulfur atom, which is 2 negative. So the formula for this ionic compound is 2 potassiums bonded to 1 sulfur. It's going to be K2S. 2 potassium ions bonded to 1 sulfur ion. And that's our ionic compound, K2S. If you recall, we name it by naming the first ion, potassium, then the second ion, but we change its name to ide. So this is potassium sulfide. Element negative ions become ide, always, when we name them. So sodium would react in a very similar way, N2S. Rubidium would react in a very similar way, Rb2S, because they all form positive 1 charges. Let's try another one. Let's try aluminum, and let's bond it with bromine. So aluminum and bromine. So aluminum, when it forms ions, will form an ion with a 3 positive charge. Bromine, when it forms ions, will gain 1 electron and form a 1 negative charge. So again, positives and negatives attract one another, and the aluminum is going to attract the bromine to it. But if you'll notice, 3 positive and 1 negative, that's not neutral. So we actually are going to need 3 bromines, each one with a negative charge, to make 3 negative charges to cancel out the 3 positive charge. So this compound is going to be AlBr3. And the name of this is going to be aluminum bromide. Notice that bromine, chlorine, fluorine, and iodine all form -1 charges. So all these elements would bond in the same way to aluminum, AlF3, AlCl3, AlI3, because they're very similar to one another. So by looking on the periodic table, we can figure out charges. The charges are due to gaining electrons, like the nonmetals, or losing electrons, like the metals, due to the low effective charge or high effective charge of the element. And elements in the same family have very similar reactivities due to their similar charges. So that's where I'm going to stop. As always, if you have questions about any of these concepts, please get in touch with me and I can explain it in more detail.